So far, I've just qualitatively described what osmotic pressure is, but we could be more quantitative about osmotic pressure and actually derive the relationship between the osmotic pressure value and concentration by considering, how the chemical potentials of alpha and beta are related. Okay? And so to do this analysis, let's define our system. Let the number 1 refer to solvent, and then the number 2 refer to solute. And so if we're just considering the chemical potentials of the solvent in the alpha phase at some temperature and pressure P naught, we'll also consider the chemical potential of the solvent in the beta phase at some pressure P naught plus the osmotic pressure. And then it's also going to be a function of the mole fraction of the solvent as well. Okay. Now, for the beta phase, this is how the chemical potentials would be related at equilibrium. For the chemical potential in the beta phase, we have here that it's a function of pressure plus osmotic pressure. But we could split up these contributions like this. So beta 1 T P naught plus, oh no, not plus, that is comma x1 for the solvent. And then to account for the change in pressure, we'll just look at the partial derivative of the chemical potential of the solvent with respect to pressure at constant P and at constant moles N1 and 2. Okay? As the pressure changes from P naught to P naught plus pi. Okay? Right, and so this is just kind of similar to what we were doing in chapters 6 and 7, where we account for changes in our different energies using partial derivatives. Okay. All right, and so to account for the change in the chemical potential on the beta side, we use this term. And so for this partial derivative, T N1 and 2, really we could kind of split it up. And so we know that by definition, the chemical potential of the solvent can be written like this, where chemical potential is just the partial derivative of the total Gibbs energy at constant temperature, pressure, and N solute. It's the partial derivative of that with respect to the moles of the solvent. Okay. All right, and so this is, the definition of this partial derivative. But using the commutative property, we could switch the order of these two partial derivatives. And so what we have now is ddn1 on the outside, and on the inside we'll have our ddp. Temperature N1 and 2, TP and 2. Okay. All right, and so now on the inside we have a dg dp. And if we remember back from the fundamental Gibbs energy equation, this partial derivative is just going to be equal to volume. Okay. And so what we have now is ddn1 for V at T, P, and 2. Okay? And so we're taking the partial derivative of the total volume with respect to the moles of the solvent. And so that also by definition, is just the partial molar volume of the solvent. So V1 bar. Okay? All right, and so now that we've shown what this term is, we can plug in this result back in here. So now we have mu1 alpha at T_P naught. We know that mu1 is just pure, or in the alpha phase, it's just pure solvent. So we could just call this the standard state chemical potential for the pure species. So that's going to be equal to mu1 beta at some temperature P naught x1 plus the integral P naught to P naught plus pi of the solvent partial molar volume dP. Since we're dealing with liquids, we could assume that the partial molar volume of the solvent is not going to be a strong function of pressure. So we'll just assume that this is a constant. Okay? And so when we perform this integral, what we're going to get is V1 here times P naught plus pi minus P naught, and then the P naughts are going to cancel. Okay? And so what we get is that the chemical potential for the pure species is equal to chemical potential in the beta compartment, T P naught x1 plus V1 bar pi. What I'm going to do now is I'm going to move this to this side and subtract off this here, so that I could write mu1 beta T P naught x1 minus the pure standard state chemical potential is equal to negative V1 bar pi. And the reason I wrote this equation like this is because here on the left hand side we essentially have the chemical potential that we of the actual mixture minus the standard state chemical potential. And so by definition, if we remember the previous videos where I talked about the chemical potential of dilute solutions, this here would just be equal to RT ln of x1. Okay? And so what I have now is that essentially we have an osmotic pressure term that now has a direct relationship to the mole fraction of the solvent in the mixture in the beta side. Okay? And so what I'll do is I'll just rearrange this equation so that pi is equal to negative RT over V1 bar ln of x1. Okay? And so now we know, because in the beta side the only things we have are solvent and solute, I could rewrite x1 as ln of 1 minus x2, still over V1 bar. Okay? All right. Now, on the beta side, even if we go back to this picture, we have both the solvent and we have the solute. But what we're doing is we're considering the case where, even though there's solute on the beta side, there isn't that much solute, right? And so it's going to be a fairly dilute solution. And so if it's dilute, that means that our x2 value is going to be pretty small. It's going to be pretty close to 0. And so since x2 is small, what we could do is for our ln of 1 minus x2 term, we could apply a Taylor series expansion. And so we could rewrite ln of 1 minus x2 as ln of 1 minus x2 equal to 0, and then plus, we then take the derivative of this and then evaluate it at 0. And so the derivative of ln of 1 minus x2 is going to be negative 1 divided by 1 minus x2, where for x2 we plug in 0. And then we multiply this term by x2. And then we also have some higher order terms that we're, since we're only care about the dilute solutions, aren't going to play that much of a factor. Okay. In any case, ln of 1 minus 0 gives us ln of 1. So this term then is going to be 0. And then here, we're just going to get negative x2, because in the denominator we have 1 minus 0. All right, and so by doing this Taylor series expansion, we get that ln of 1 minus x2 is essentially, or approximately, equal to negative x2. And so now our pi equation is going to be minus RT minus x2 over v1 bar. So now we have RT over x2 over v1 bar. Okay, and so once again, now we have a relationship between the osmotic pressure and now the mole fraction of solute in the beta compartment. There's one more thing I'm going to do here. Traditionally or conventionally, when we consider osmotic pressure, rather than looking at mole fractions, we actually care more, or usually evaluate it based on the absolute concentration of solute in the beta compartment. Okay, and so what I want to do here is I want to convert this mole fraction into a concentration value. Okay, and so for the mole fraction x2, we know that that's basically just the moles of the solute divided by the total moles. Now, since we're dealing with a dilute solution, N1, which is the moles of solvent, are going to be much larger than N2, which is the moles of the solute. And so essentially our denominator term is just going to be equal to the moles of solvent. And so x2 is approximately just N2 divided by N1. Now for each of these moles, for the moles of the solute, that's going to be equal to our molar concentration, C2, times the total volume of the beta compartment. And for N1, we could write that in terms of the partial molar volume of the solvent. And so that would just be V divided by V1 bar. These V's cancel, and so we get that x2 is approximately just equal to C2 times V1 bar. We now go back and plug that into our pi equation, and we get that our osmotic pressure is equal to RT C V1 bar over V1 bar. These V1 bars cancel, and what we get is that osmotic pressure is just equal to C2 R times T, which is exactly what's observed experimentally. All right? And so just as a reminder, this C2 term is moles of solute over the total volume of the beta compartment, or the system that you care about. All right, and so, going through by relating the chemical potentials of the alpha and the beta compartment, we were able to develop an equation that relates the osmotic pressure of the beta side, that kind of hypothetical theoretical pressure you need to apply to the beta side in order to stop solvent from flowing. We could relate that to the concentration of solute in that compartment. All right? And I just want to emphasize that this result we got was based on the assumption that we were dealing with a dilute concentration of the solute in the solvent. If you're dealing with more concentrated mixtures, then you would have to add on terms that account for sort of non-idealities.